Close your eyes now and let your breathing slow, because tonight we are not going anywhere fast. Tonight we are going somewhere very, very far, but we are going to go there slowly, the way a boat drifts from a dock without anyone pushing it, just the water deciding to carry it away. Somewhere above you, past the ceiling, past the roof, past the clouds if there are any tonight, past the moon and past the sun and past every star you have ever been able to point at with a tired finger, there are places in the universe so quiet and so dark that light itself, which is the fastest thing there is, the thing that can circle the entire Earth 7 times in a single second, simply cannot find its way back out. We call these places black holes, and there is nothing to be afraid of in that name, not tonight, because we are only going to visit them the way you visit a dream, drifting in, looking around, and drifting out again whenever you like, usually somewhere around the part where your eyelids get too heavy to keep this up. A black hole is not really a hole in the way a hole in your sock is a hole, a gap where something used to be. It is more like an extremely patient knot tied into the fabric of space itself, a place where gravity has folded so much distance into so little room that anything nearby, light included, slides toward the center and never finds a way to slide back out. Imagine a blanket stretched tight between 2 people, and imagine setting a marble in the middle and watching the blanket dip. Now imagine setting something impossibly heavy there instead, something so heavy that the dip becomes a well, and the well becomes a tunnel, and the tunnel becomes so steep and so deep that it stops looking like a dip in a blanket and starts looking like the blanket has simply run out of room to describe what is happening. That is a very small, very soft way of picturing gravity near a black hole, and it is wrong in 100 technical ways that no scientist would let you get away with in the daytime. But at night, drifting towards sleep, it is exactly the right amount of true. Most black holes are born from stars, and this is one of the gentle secrets of the universe, that endings are often just very slow beginnings wearing a different coat. A star spends its whole long life in a kind of contest between 2 forces that never stop pulling against each other. Gravity always trying to crush the star down into the smallest possible ball, and pressure from the nuclear fire in its belly always pushing back out, holding the shape open, keeping the star round and bright and stable for millions or billions of years, depending on how big it started out. But fuel runs low eventually, the way a fire in a fireplace runs low near the end of a long winter night, and when the pushing stops, the crushing wins. For an ordinary star like our sun, this ending is calm, a slow settling into a small glowing coal called a white dwarf that will cool for longer than the universe has even existed so far. But for a star many times more massive than our sun, the ending is anything but calm and anything but slow. The core collapses in less than a second, falling in on itself faster than you could say the word gravity, and the outer layers explode outward in a supernova bright enough to outshine an entire galaxy for a few weeks, visible across billions of light years, a final enormous exhale after a life of enormous inhales. And in the very center of that explosion, if the collapsing core was heavy enough, gravity wins so completely that nothing is left to stop it, and a black hole is born in the silence after the fireworks, small and dark, and settling quietly into the space where a star used to be. You might think something so violent in its birth would announce itself forever, but a black hole is one of the quietest objects in the universe once it settles in. It does not glow. It does not shine. It does not make a sound, because sound needs air or gas or something to travel through, and space between the stars is mostly a hush of near-perfect emptiness. A black hole simply sits there, curving the space around it, waiting the way a held breath waits, patient in a way nothing alive could ever manage, patient across spans of time that make a human lifetime look like the blink of an eye, or less than that, like the time between one blink and the thought of blinking. There is a boundary around every black hole called the event horizon, and this is perhaps the gentlest and strangest idea in this whole quiet story. The event horizon is not a wall, not a surface, not anything you could touch or bump into or feel yourself pass through. It is simply the last place where leaving is still possible. 1 inch closer to the center than the event horizon, and even light, moving at the fastest speed the universe allows, cannot climb back out, the way you cannot unfall down a hill once your feet have already left solid ground and gravity has already made its decision for you. 1 inch farther out than the event horizon, and light escapes just fine, drifting away into the dark to eventually reach some distant eye, some distant telescope, some distant sleepy person wondering what they are looking at. The event horizon is simply the softest, most invisible line in existence, a line with no fence and no color and no sound, and yet it is the most absolute boundary anything can ever cross, because once you are on the inside, there is no version of physics, no rocket engine, no clever idea that lets you cross back to the outside again. Here is a strange and cozy thought to carry with you as you sink further into the pillow. If you could somehow fall toward a very large black hole, one large enough that the tides of gravity would not stretch you apart before you got there, you might cross the event horizon and notice absolutely nothing unusual happening to you in that exact moment. No bump, no flash, no sudden change in temperature or light. You would simply be falling, the way you fall in an elevator when the cable is cut, weightless and calm, and it is only later, once you tried to check your watch against someone far away, that you would discover time itself had started behaving differently for you than for them, stretching and slowing the way a held note stretches at the end of a lullaby, quieter and slower and longer than you expected, until from the outside it would look as though you were slowing down forever, never quite finishing your fall, fading softly instead of vanishing all at once. This is one of the dreamiest facts in all of physics, that falling into a black hole looks completely different depending on whether you are the one falling or the one watching from far away and safely tucked into your own soft bed. Time near a black hole is not the steady, dependable river we like to imagine on ordinary nights. Time bends, the way a road bends around a mountain, and the closer you get to a black hole, the more that road curves, until right at the edge, at the event horizon itself, time as measured by someone far away appears to stop completely, freezing that last visible glimmer forever, even though for the falling traveler no such freezing happens at all, and their personal clock ticks along in perfectly ordinary rhythm all the way down. Two truths, both correct, both measured honestly, and neither one canceling the other out, simply two different vantage points on the same strange and gentle event. The way two people describe the same dream differently depending on which part they remember best when they wake. Let your mind drift now to the very center. If a black hole can even be said to have a center in the way an apple has a center. According to the equations that describe gravity at its simplest and most elegant, everything that falls into a black hole is eventually crushed down into a single point of infinite density called a singularity. A place where all the usual rules of physics quietly raise their hands and admit they do not know what happens next. Nobody has ever seen a singularity, and nobody ever will, because it hides forever behind the event horizon, wrapped in secrecy the way a gift is wrapped in paper you are never allowed to remove. Many physicists suspect that the true story of the very center is not really an infinite point at all, but something gentler and stranger that our current equations are simply not refined enough yet to describe. Some deeper layer of reality waiting patiently to be understood. The way a bedtime story sometimes hints at a sequel it never quite gets around to telling. Black holes come in sizes that might surprise you, the way finding out how many kinds of clouds there are might surprise you on a lazy afternoon. There are stellar black holes, born from the collapse of massive stars, typically weighing somewhere between about 5 and a few dozen times as much as our sun. Though squeezed down into a region only a few miles across, smaller than most cities, holding all that mass in a space you could almost imagine driving across before breakfast, if driving into a black hole were the kind of thing anyone should ever attempt. There are supermassive black holes, hiding at the center of nearly every large galaxy, including our own, weighing millions or even billions of times as much as the Sun. And yet, in a strange twist that feels almost like a lullaby's gentle joke, the biggest black holes are in some ways the calmest ones to imagine, because their sheer size actually makes the space near their event horizon less violently curved than the space near a small stellar black hole. Meaning, if you had to fall into a black hole and survive the actual crossing of the horizon without being stretched apart by tides, you would want to choose the biggest one you could find, not the smallest. Our very own Milky Way galaxy cradles a supermassive black hole at its heart, a quiet giant named Sagittarius A star, weighing about 4 million times as much as our Sun, sitting there in the crowded, glittering center of the galaxy, about 26,000 light-years from where you are lying right now, wrapped in blankets, listening to this. It does not reach out and pull in nearby stars the way it is sometimes dramatically pictured. Most stars orbit it peacefully, the way planets orbit a sun, dancing slow orbits that take decades or centuries to complete, kept at a respectful and stable distance by the same laws that keep our own Earth calmly circling our own sun instead of spiraling into it. Astronomers have watched individual stars trace out their orbits around this quiet giant over the years, and from those graceful, patient orbits, calculated just how heavy the invisible thing at the center must be, proving its existence not by seeing it directly, since by definition you cannot see a black hole, but by watching everything nearby dance around an emptiness that behaves exactly the way a great and hidden weight should behave. In the spring of 2019, humanity saw, for the very first time, an actual image of the environment around a black hole, not the black hole itself, which remains and will always remain invisible, but the glowing, swirling ring of hot gas and light bent dramatically around the dark shadow of its event horizon, a picture assembled from radio telescopes scattered across the entire planet. All listening together, as if the whole Earth had turned into a single, enormous ear pressed against the sky. The black hole in that first picture lives at the center of a galaxy called M87, more than 50 million light-years away, so large that its shadow, glowing amber and gold around a perfectly dark center, looks something like a very slow, very patient eye blinking open after waiting 55 million years for someone far away to finally build the right kind of telescope to notice it looking back. Let yourself sink a little deeper now, past the picture, past the telescopes, down into the quieter question of what a black hole actually does to the things that wander too close but have not yet crossed the point of no return. Gravity, as you already know from ordinary nights of dropping a spoon or missing a step in the dark, pulls harder the closer you get to something heavy. Near an ordinary object like a planet or a person, that difference in pull from one end of your body to the other is so small you never notice it. Your head and your feet basically agreeing on how strong gravity feels. But near a small, dense black hole, that difference becomes enormous over even a short distance. So enormous that if you fell in feet first, your feet would feel a pull many times stronger than your head, stretching you gently at first, and then not so gently, longer and thinner, the way a piece of soft taffy stretches between two slow hands, until scientists, who apparently allow themselves exactly one joke in this entire, otherwise serious field, decided to name this stretching effect spaghettification. Because that is more or less the shape you would end up in. This is not a pleasant fact, but it is a dreamy one in its own strange way, a reminder that far away, in the hush of deep space, geometry itself can reach out and rearrange you the way a slow tide rearranges sand. Not every black hole simply sits still and quiet, either. Many of them spin, inherited from the spin of the star that collapsed to form them, the way a figure skater spins faster by pulling their arms in close. A spinning black hole drags the space around it in swirling loops, an effect so gentle and so real that it has an official name, frame dragging, as though space itself were a great slow whirlpool being stirred by an invisible spoon at the center. Around a spinning black hole, there is a region called the ergosphere, just outside the event horizon, where this dragging is so strong that nothing, not even light, can stay still relative to the distant stars. Everything caught there is swept along in the spin whether it wants to be or not. The way a leaf caught at the very edge of a stream is tugged forward even if it never quite falls into the deepest part of the current. And yet, strangely, gently, it is still possible to enter the ergosphere and leave again, unlike the event horizon itself. And some physicists have imagined that a sufficiently clever traveler could even use this spinning region to steal a little energy from the black hole's spin and fling themselves back out again faster than they went in. A theoretical trick called the Penrose process, a bit of cosmic momentum borrowed. Like taking a running push off a merry-go-round that never even notices you were there. Most black holes we actually observe are not silent and invisible at all, at least not from a distance, because they are usually surrounded by a hot, glowing disk of gas and dust called an accretion disk, material that used to be minding its own business somewhere in a galaxy and slowly spiraled inward, pulled by gravity into a flattened, swirling shape, much like water spiraling gently around a drain, except here the water is made of stripped atoms and dust and starlight. And the drain never actually seems to empty because there is always more material arriving from farther out. As this material spirals closer and closer, friction and compression heat it to unimaginable temperatures, so hot that it glows brightly not just in visible light but in X-rays. And this is, in fact, the main way astronomers find black holes at all, not by seeing the dark shape itself, but by seeing the bright, feverish glow of everything swirling just outside it. The way you might notice a dark doorway at night, not because you can see into the room, but because you can see the light spilling out around its edges from something happening just inside. Some of the most energetic objects in the entire universe are powered by exactly this process. Supermassive black holes feeding on enormous amounts of gas, blazing so brightly across billions of light years that for decades astronomers mistook them for single, impossibly bright stars, naming them quasars, short for quasi-stellar radio sources, before realizing that no single star could ever outshine an entire galaxy of hundreds of billions of stars combined. Which is exactly what these quasars do, sitting at the hearts of young, distant galaxies, feeding and glowing, and occasionally launching enormous jets of matter squeezed out along their spin axis at nearly the speed of light, streams so long and so straight they can stretch for hundreds of thousands of light years, farther than the entire width of our galaxy. Thin glowing threads reaching out into the darkness like the world's longest exhale. Here is a fact that feels almost like a secret passed quietly under a blanket after the lights are already off. In 1974, a physicist named Stephen Hawking, thinking very carefully about the strange border where the rules of gravity and the rules of quantum mechanics both try to apply at once, realized that black holes are not actually eternal and unchanging after all. Right at the fuzzy edge of the event horizon, the vacuum of space is not perfectly empty, but instead fizzes gently with pairs of particles winking briefly into existence, and then just as quickly disappearing again. A kind of endless, silent, cosmic static too faint for us to ever notice under ordinary circumstances. But right at a black hole's edge, it becomes possible for one particle of such a pair to fall in while its partner escapes outward, carrying a tiny sliver of energy away with it. And when you add up this leaking over immense stretches of time, it means every single black hole in the universe is very, very slowly evaporating, glowing ever so faintly with what we now call Hawking radiation, losing mass so gradually that even the smallest known black holes would take far longer than the current age of the universe to noticeably shrink, and the largest supermassive ones would take a span of time so long that the number itself becomes almost meaningless to say out loud, longer than anything else in this story. A slow fade toward nothing that will likely be the very last event of any consequence to happen anywhere in the universe. Long after the stars have all gone dark and the galaxies have all drifted apart, one last, faint, patient sigh escaping into an emptiness that no longer has anyone left to hear it. And yet even that faint leak of radiation has caused one of the deepest and most stubborn puzzles in modern physics, something called the black hole information paradox, a puzzle so persistent that physicists have been arguing gently about it, in the nicest and most rigorous way scientists know how to argue, for decades. Ordinary physics insists that information can never truly be destroyed, that if you burn a letter to ash, the information describing every word on that page is not gone, only scrambled so thoroughly into smoke and heat and light that nobody could ever practically piece it back together. But in principle, if you could track every single particle, you could still reconstruct the original letter. Black holes seem to break this rule, because if a black hole eventually evaporates away completely through Hawking radiation, and that radiation looks completely random with no trace of what fell in to create it, then the information about everything that ever fell into that black hole, every star, every wandering asteroid, every unlucky astronaut, appears to vanish from the universe entirely and forever, something the deepest laws of physics insist should be impossible. Nobody has fully solved this puzzle yet, though there have been beautiful, hopeful glimpses of an answer in recent years involving strange, twisted geometric shapes physicists call islands hidden inside the mathematics of the radiation itself, suggesting that the information may be smuggled out after all, encoded so subtly and so thoroughly scrambled into the outgoing glow that it only looks random, the way a lullaby sung backward might still. If you listened closely enough and knew exactly what to listen for, carry every note of the original song. There is a kind of music the universe makes that has nothing to do with sound at all, and black holes turned out to be some of its finest instruments. When two black holes spiral around each other, closer and closer over millions or billions of years, they stir up ripples in space and time itself, tiny stretching and squeezing waves called gravitational waves, spreading outward in every direction like rings on a pond, except the pond here is the fabric of the universe, and the pebble is two invisible giants dancing an ever-tightening waltz. For 100 years after Einstein first predicted these ripples, nobody had ever detected one, because by the time they cross the unimaginable distances of space and reach us, they have weakened to a motion smaller than the width of a single proton, a stretch and squeeze so gentle it seemed impossible any instrument could ever notice it. And yet in September of 2015, twin detectors called LIGO, built with mirrors hung so carefully, and lasers aimed so precisely that they could sense a change in distance a tiny fraction of the width of an atomic nucleus, felt exactly that, a faint chirp rising in pitch and volume over a fifth of a second. The sound, if you sped it up into the range human ears can hear, of two black holes each about 30 times heavier than our sun, colliding over 1 billion light-years away. Merging into one and briefly outshining, in pure gravitational energy, every star in the visible universe combined, unseen by any eye, felt only as this soft rising chirp captured by patient instruments built by patient people who had waited decades for exactly this whisper to arrive. Since that first detection, gravitational wave observatories have caught dozens and then hundreds of these cosmic chirps, black holes merging with other black holes merging with the dense collapsed cores of dead stars called neutron stars, whole quiet catalogs of collisions happening constantly throughout the universe, far more often than anyone expected, a steady faint drumbeat underlying everything, felt only by machines built specifically to feel it. A reminder that even in the deepest silence of space, in the parts of the universe with no air to carry sound and no ears to hear it anyway, there is still a kind of motion happening, a kind of rhythm, patient and enormous and slow, that we only very recently learned how to notice at all. Black holes are wonderfully, almost embarrassingly simple objects once you actually manage to describe one completely, and this simplicity has its own gentle name among physicists, the no-hair theorem, a playful way of saying that no matter how complicated and messy and interesting the star or the gas cloud, or the collapsing cluster of stars that formed a black hole once it settles down behind its event horizon, the black hole itself can be described completely using only three numbers: how much it weighs, how fast it spins, and whether it carries any electric charge, which in practice is almost always none at all, since charged matter tends to attract its opposite and neutralize quickly. Every other detail, every bump and lump and asymmetry the original star ever had, is smoothed away and forgotten forever, radiated off as gravitational waves in the last violent moments of collapse, leaving behind something almost perfectly plain and featureless: a sphere, or a slightly flattened spinning sphere, holding no memory, no fingerprint, no trace of its own dramatic past, the calmest possible resting shape for something built from the most violent event a star can experience. Not all black holes are created the slow, familiar way, through the collapse of a dying star, either. Some physicists suspect that in the first fraction of a second after the universe itself began, when everything was compressed into a hot, dense, churning froth far denser than any star could ever become, tiny fluctuations in that early density might have been enough, in certain rare pockets, to collapse directly into black holes without ever needing a star at all. These are called primordial black holes, and if they exist, they could range from impossibly tiny, lighter than a mountain and smaller than an atom, up through sizes we have never otherwise observed in nature. And some researchers have wondered, quietly and without full proof yet, whether a scattered population of these ancient, invisible objects might make up some portion of the mysterious dark matter that outweighs all the visible stars and galaxies combined. Ancient relics from the universe's very first heartbeat, drifting unseen through space ever since, older than any star, older than any galaxy, nearly as old as time itself. Between the smaller stellar black holes and the enormous supermassive ones sitting at galactic centers, there is a size range astronomers have had a surprisingly hard time finding examples of, called intermediate mass black holes, weighing somewhere between 100 and 100,000 times as much as the Sun. For years, this size range was almost suspiciously empty of confirmed examples, a quiet gap in an otherwise fairly continuous family. And only in recent years, through careful gravitational wave detections and patient searches in dense star clusters, have astronomers begun to find convincing candidates filling in that gap, suggesting these middle-sized black holes may form when several smaller black holes wander close enough together in a crowded cluster to merge repeatedly. Growing step by step, generation by generation, the way a snowball grows not from one dramatic scoop, but from many small ones rolled together over a long, unhurried afternoon. Galaxies and the supermassive black holes at their hearts appear to grow up together in a strange kind of partnership, each one shaping the other across billions of years, in ways astronomers are still gently working out. The mass of a galaxy's central black hole tends to match, in a fairly consistent ratio, the mass of the great swirling bulge of stars around it, as though the two had been listening to each other's growth the whole time and packing themselves accordingly, even though a black hole's own gravity only reaches a relatively small distance compared to the vast scale of an entire galaxy. When a supermassive black hole feeds actively, blazing as a quasar, the fierce light and outward-blowing winds it generates can push back on the surrounding gas clouds throughout the galaxy, gently discouraging new stars from forming in some regions while shaping the flow of material in others. A kind of slow conversation between the smallest, densest point in a galaxy and the sprawling, glittering whole, neither one entirely in control, both quietly influencing the other's fate across timescales longer than any single human life could ever witness beginning to end. Sometimes an unlucky star wanders too close to a supermassive black hole without actually falling all the way in, and the result is one of the more dramatic and yet oddly graceful events astronomers have learned to watch for, called a tidal disruption event. The black hole's gravity, so much stronger on the near side of the star than the far side, stretches the star apart the same way it would stretch a falling person, except at a scale spanning the entire star, tearing it into a long glowing thread of gas that wraps around the black hole in a bright, brief flare visible across enormous distances. A last, dramatic scattering of light before roughly half the star's material eventually falls in, and the other half is flung back out into space, scattering out into the dark to become, perhaps, the raw beginnings of some future star, some future planet, some far distant future night sky that some other sleepy creature somewhere might eventually look up at, without ever knowing where the light of those particular atoms first came from. Gravity around a black hole does something else, quieter and lovelier than any collision, something you can genuinely see with an ordinary telescope even from an enormous distance, called gravitational lensing. Light traveling from a distant galaxy, if it happens to pass near enough to a black hole or any sufficiently massive object on its long journey toward us, gets bent by the warped space around that mass, the way light bends passing through a lens of curved glass, and sometimes this bending is strong enough to produce multiple smeared or duplicated images of the very same distant galaxy, arranged in rings or arcs or strange repeated clusters around the closer massive object. A kind of natural magnifying glass built entirely out of gravity, letting us see galaxies so distant and so faint that no telescope could ever have spotted them directly, all thanks to an invisible, patient bit of geometry bending their light gently on its way toward our waiting eyes. People sometimes worry, in the quiet hours right before sleep, whether a black hole might someday wander into our solar system and swallow the Earth the way it swallows everything else nearby. And this is a good moment, drifting along in this soft, dark story, to let that particular worry go entirely. The nearest known black hole to Earth sits roughly 1,000 light-years away, and even if a stray one somehow drifted closer, a black hole is not a vacuum cleaner reaching out through all of space. It only pulls on things the same amount that any object of equal mass would pull on them from the same distance, meaning if our sun were somehow magically replaced overnight with a black hole of exactly the same mass, changing nothing else, the Earth would keep orbiting in exactly the same circle it always has, just considerably colder and darker, which would admittedly be its own kind of problem. But not the dramatic swallowing sort of problem most people imagine when they hear the words black hole late at night. Let yourself drift now toward the very edge of what physics is confident about, and what physics only whispers as a hopeful guess. Some equations describing black holes technically allow for the existence of wormholes, theoretical tunnels connecting one point in space and time to a completely different point, perhaps even a different universe entirely, folding the impossibly long journey between two places into a single, short, improbable step. No wormhole has ever been observed, and most physicists suspect that even if the equations allow them on paper, nature has no practical way of actually building or holding one open, since doing so seems to require some exotic form of matter or energy that pushes rather than pulls. A kind of anti-gravity glue holding the tunnel from collapsing shut the instant anything tried to pass through it. But it remains one of the loveliest, dreamiest ideas to fall asleep turning over in your mind. The thought that somewhere in the deep architecture of the equations describing gravity, there might be a shortcut stitched quietly between two otherwise unreachable corners of everything that exists, waiting, unused and perhaps unusable, like a door drawn on a map that nobody has ever actually found the key to. Long before anyone had proof that black holes were real, the idea of them had already drifted quietly through the minds of a few thoughtful people, patient guesses made in the dark long before any telescope could confirm them. Back in 1783, an English clergyman and scientist named John Michell wondered, on paper, using nothing but Isaac Newton's ordinary laws of gravity, what would happen if a star were simply massive enough and dense enough that its own escape velocity, the speed something would need to break free of its gravity forever, exceeded the speed of light itself. He called the idea a dark star, reasoning quietly that light leaving such an object would be pulled back the way a ball thrown to gently falls back to the ground, and that we would never see such a star directly at all, only perhaps notice its gravity tugging at whatever happened to orbit nearby. A French mathematician named Pierre-Simon Laplace arrived independently at a similar thought a few years later, and then the idea rested, quiet and mostly forgotten, for more than a century, waiting the way a seed waits underground through a long winter, until Albert Einstein published his equations of general relativity in 1915 and gave the whole idea a far deeper and stranger mathematical home to grow in. It took only a matter of months after Einstein's equations were published for a German physicist named Karl Schwarzschild, serving on the front lines during the First World War, to find, almost unbelievably quickly, an exact solution to those famously difficult equations describing the space around a single, simple, non-spinning mass, a solution that produced, tucked inside its own mathematics, exactly the strange boundary we now call an event horizon. Schwarzschild sent his solution back from the war to Einstein by letter, and Einstein presented it to the Prussian Academy of Sciences on his behalf. And then, only a few months later, Schwarzschild died of an illness contracted at the front, never living to see how central his quiet, careful bit of mathematics would become to an entire field of astronomy that did not even have a name yet for the strange objects his equations predicted. For decades afterward, most physicists, including Einstein himself, treated the Schwarzschild solution's strange central point and stranger boundary as a mathematical curiosity, an oddity unlikely to correspond to anything real, the way a strange shape appearing briefly in a dream is rarely mistaken for an actual place. It was not until the 1960s, and a physicist named John Wheeler helping popularize a punchy, memorable name, that the phrase black hole finally caught on and stuck, giving a simple, almost gentle name to an object built from some of the most extreme mathematics ever written down. There is a strict and careful rule inside the mathematics of black holes called the law of cosmic censorship, a name that sounds almost stern for such a quiet idea, which simply states, as a strong working assumption physicists still cannot fully prove in every possible case, that nature always politely hides its singularities behind an event horizon, never leaving one exposed and naked to the outside universe. A naked singularity, if one could somehow exist unshielded by any horizon, would be a point where the predictable, orderly rules of physics simply broke down out in the open, in principle visible and reachable, a place where cause and effect themselves might come unstitched. And most physicists find this idea so deeply uncomfortable to the tidy logical structure of physics that they suspect, though cannot yet fully prove, that the universe simply does not allow it. Tucking every one of its infinitely dense, infinitely strange points safely out of sight, the way a considerate host tucks away the messiest, most complicated parts of a home before any guest arrives, letting the visible universe stay comparatively calm, orderly, and dreamable. Black holes, strangely enough, obey their very own quiet version of the laws of thermodynamics, the same family of laws that governs how heat flows and how ice melts, and how a warm cup of tea slowly cools to match the room around it. A physicist named Jacob Bekenstein realized in the early 1970s that a black hole's event horizon has an area that only ever grows or stays the same, never shrinks, whenever ordinary matter falls in, matching almost exactly the behavior of something physicists call entropy, a measure of disorder that the universe as a whole never seems to decrease either. Stephen Hawking, initially skeptical, worked out the mathematics carefully enough to realize Bekenstein was onto something remarkably real, and together their combined insight now carries a shared name, Bekenstein-Hawking entropy, describing the astonishing fact that a black hole holds, hidden behind its horizon, more disorder, more hidden information capacity than nearly any other object of the same size in the entire universe. an object built from almost nothing but empty curved space turning out to be, by this strange thermodynamic measure, one of the most information-dense things that can possibly exist. The very edge of what a distant observer can actually see of a black hole is called its photon sphere, a delicate, invisible shell of space, slightly farther out than the event horizon itself, where gravity curves space so sharply that light can, in principle, travel in a perfect circle around the black hole forever, chasing its own tail in an endless, silent, glowing orbit. In practice, this perfect balance is unstable. The way balancing a pencil on its very tip is technically possible but never really lasts, and any light drifting through the photon sphere either slowly spirals inward to be lost forever or slowly spirals back outward to escape. But for one shimmering, theoretical instant, right at that perfect radius, a beam of light could circle a black hole again and again, and it is this photon sphere, bending and gathering light from every angle around the black hole, that produces the bright glowing ring astronomers actually photograph, an echo of geometry so precise it can be calculated in advance, and then, one patient day in 2019, actually seen. Somewhere out past the edge of ordinary stars, there sits a very particular and very famous black hole named Cygnus X1, one of the first objects ever strongly suspected to be a black hole rather than merely a strange, unusually bright source of X-rays, discovered by satellites listening for X-ray light in the early 1960s, and the subject, for many years afterward, of a friendly and famous scientific wager between Stephen Hawking, who bet against it being a black hole, apparently as a kind of insurance policy so that if black holes turned out not to exist after all the years he had spent studying them would not feel entirely wasted, and another physicist, Kip Thorne, who bet in favor. By the mid-1990s, evidence had grown overwhelming, and Hawking conceded the bet, buying Thorne a subscription to a magazine as agreed, a small, warm, human footnote tucked quietly into the history of one of the most extreme objects in the observable universe. Somewhere far across the observable universe, near the very edge of what our best telescopes can currently detect, sits an object named TUN 618, among the heaviest black holes humanity has ever measured, weighing something on the order of 66 billion times as much as our Sun, a number so large it stops feeling like a number at all, and starts feeling more like a kind of weather, an entire small galaxy's worth of mass folded down into a single, dark, patient point, glowing at its edges as a quasar so bright it remains visible across billions of light years of perfectly empty, perfectly dark space in between, a single distant candle burning steady enough to be seen from almost the very beginning of time. Curious minds sometimes wonder whether powerful particle colliders here on Earth, the enormous machines that smash tiny particles together at nearly the speed of light to study the fundamental building blocks of matter, might accidentally create a tiny black hole in the process. And this thought, while dramatic enough to make headlines now and then, turns out to be one of the gentler worries you can safely let go of tonight. Any black hole tiny enough to be created by such a collision would carry so little mass that Hawking radiation, that same slow leaking glow discovered decades ago, would cause it to evaporate away again in a tiny, harmless fraction of a second, far faster than it could ever grow by pulling in surrounding matter. And in any case, cosmic rays far more energetic than anything human machines can currently produce have been striking the Earth's atmosphere harmlessly for billions of years without incident. A long, quiet, natural experiment already run for us by the universe itself, long before any laboratory existed to worry about repeating it. A black hole and its quieter, only slightly less extreme cousin, the neutron star, are born from strikingly similar circumstances, both left behind after a massive star's core collapses at the end of its life, and the difference between which one you end up with comes down mostly to a matter of weight. If the collapsing core is left with a little less than about 3 times the mass of our Sun, The crushing pressure is eventually stopped by an intense quantum mechanical resistance between densely packed particles called neutrons, resulting in a neutron star, an object so dense that a single teaspoon of its material would weigh roughly as much as a mountain, spinning sometimes hundreds of times each second, and sweeping a lighthouse beam of radio waves across the galaxy as it turns. But if the collapsing core weighs more than that critical threshold, even the fierce resistance of tightly packed neutrons is not enough, and the collapse continues all the way down into a black hole, meaning that somewhere in the universe, quietly, there is an exact dividing line, a specific number of solar masses, on one side of which a star's leftover heart becomes a spinning, glowing lighthouse, and on the other side becomes an object that emits no light at all. A strange and delicate kind of fork in the road, decided entirely by how much of the original star happened to be left over after everything else had already burned away. When two black holes finally spiral together and merge, the event is rarely perfectly symmetrical, and sometimes the newly formed, larger black hole receives a surprisingly strong kick, a recoil not unlike the way a rifle recoils when it fires. Except here, what is being fired is not a bullet but a lopsided burst of gravitational waves themselves, carrying away momentum in one favored direction and pushing the merged black hole in the opposite direction hard enough, in some rare configurations, to send it flying out of its host galaxy entirely at speeds of thousands of kilometers each second, a newborn black hole exiled from the very cluster of stars that built it, drifting now alone through the vast quiet space between galaxies, carrying no light, no company, and, if the no-hair theorem holds, no memory at all of the dramatic dance that flung it out there in the first place. This raises the gentle, slightly haunting idea of rogue black holes, ones that formed inside a galaxy or a dense star cluster, and were later flung out through a recoiling merger or a close gravitational encounter with other massive objects, now drifting silently through open intergalactic space, entirely invisible, revealing themselves only on the rare occasion that they happen to pass directly in front of a distant star or galaxy from our point of view, bending that background light just briefly and just slightly through gravitational lensing, a fleeting flicker that astronomers can sometimes catch and measure, calculating from the shape and duration of the flicker alone that something dark and massive and utterly silent passed through that patch of sky, unseen before and unseen ever again, a wanderer glimpsed for a single night, and then lost again to the dark for the rest of time. Physicists curious about the deepest mathematics of black holes have found a strange and delightful way to study some of their properties without ever needing an actual black hole at all, by building small, careful laboratory setups here on Earth called analog black holes. In certain flowing fluids, sound waves behave remarkably similarly to how light behaves near a real gravitational event horizon. If the fluid flows fast enough past a certain point, sound waves downstream of that point can never travel back upstream against the current, trapped exactly the way light is trapped inside a true event horizon, giving physicists a strange, gentle tabletop echo of the real thing. Cold water or ultra-cold clouds of atoms in a laboratory standing in for the impossibly distant and impossibly extreme gravity of an actual collapsed star, letting careful listeners study, in miniature and in perfect safety, some of the same physics that governs the darkest objects in the universe. Black holes are sometimes confused with dark matter, and it is worth gently untangling the two before drifting further into sleep. Because although both are invisible and both exert gravity, they are almost certainly very different things. Dark matter, whatever it ultimately turns out to be, appears to be spread out in enormous, gentle, roughly spherical clouds called halos, surrounding entire galaxies and reaching far beyond the visible edges of their swirling stars, far too smoothly spread out and far too abundant to be explained by black holes alone, at least according to the careful measurements astronomers have managed so far. And while a small fraction of dark matter conceivably could turn out to be primordial black holes formed in the universe's earliest moments, most physicists currently believe dark matter is instead made of some entirely new kind of particle, one that barely interacts with ordinary matter or light at all except through gravity, patiently outweighing every star and every black hole and every planet combined by a wide margin, and yet somehow never once directly observed. Its identity, one of the largest remaining open questions in all of modern science, quietly waiting its turn to be solved. Way back near the very beginning of the observable universe, less than 1 billion years after everything started, astronomers have found quasars already blazing away, powered by supermassive black holes already weighing billions of times as much as our sun. And this early abundance poses a lovely, difficult puzzle. There does not seem to have been enough time, by the ordinary slow process of stars collapsing and then gradually growing through mergers and feeding, for black holes to have grown so enormous so quickly after the universe began. Some astronomers suspect that certain rare, enormous clouds of primordial gas may have collapsed directly into massive black hole seeds without ever passing through an ordinary stellar phase at all, skipping several patient steps of growth the way a seed might, in some rare and lucky patch of soil, sprout directly into a full-grown tree overnight, while other astronomers suspect mergers happened far more quickly and far more often in the crowded, busy, young universe than they do today. Each explanation still being carefully weighed against the growing pile of evidence collected by ever more powerful telescopes peering ever further back toward the beginning of everything. Every so often, a gravitational wave detection arrives paired with a burst of ordinary light or other radiation from the very same distant event, a rare and treasured combination astronomers call multi-messenger astronomy, allowing two completely different kinds of evidence, the stretching and squeezing of space itself and the more familiar glow of photons, to be read together like two witnesses to the very same quiet, distant event, confirming and enriching each other's stories in ways neither could manage entirely alone. One particularly celebrated example arrived in 2017, when gravitational wave detectors and telescopes around the world both caught, within seconds of each other, the signal from two neutron stars colliding, an event that not only confirmed decades of careful theoretical prediction, but also revealed, glowing in the wreckage of that collision, freshly forged atoms of gold and platinum and other heavy elements, meaning that some of the very jewelry people wear quietly around their necks and wrists may ultimately trace its origin back to an ancient, violent, beautiful collision between two collapsed stars, light and metal both born from the same distant, silent crash. The black hole image captured in 2019 was, quietly and without much fanfare compared to its famous predecessor, followed in 2022 by a second historic image, this time of Sagittarius A star itself, the gentle giant sleeping at the center of our own Milky Way, requiring even more painstaking work to assemble than the first image had, since gas swirling around our own galaxy's central black hole moves and changes shape within minutes rather than days, smearing and blurring the picture the way a long camera exposure blurs a person who cannot quite manage to sit perfectly still, and only through extraordinarily clever processing, essentially averaging together thousands of individual snapshots taken over many nights, did astronomers finally manage to freeze that flickering, shifting glow into a single, clear, glowing ring, confirming that the quiet, invisible giant 26,000 light-years away, the one whose stars we have watched dance in patient orbits for decades, does indeed look exactly the way the equations always said it should, gravity itself photographed at last, twice now, in two completely different galaxies, each time behaving exactly as predicted, each time gently, quietly, beautifully confirming a set of equations written down more than a century earlier by someone who never once got to see a single actual picture of what he had described. Let your mind rest now on scale for a moment, the way you might rest your eyes on the ceiling without really focusing on anything. because scale is one of the hardest parts of this whole quiet story to hold onto, and also one of the most soothing once you stop trying to hold it tightly and just let it wash over you instead. If you shrank the Earth down to the size of a marble, the black hole at the center of our galaxy would still be, at that same shrunken scale, roughly the size of a large beach ball, but sitting more than 100,000 miles away from that marble, farther than our actual moon, and everything in between, every planet, every asteroid, every comet would be nothing but empty, patient dark. If you shrank the sun down to the size of a black hole of the same mass, without changing its weight at all, it would become a sphere only about 4 miles across, small enough to tuck neatly inside the boundaries of a modest city, and yet it would still weigh exactly as much as it does now, still tug at the Earth with exactly the same gravity it always has. A reminder that black holes are not measured by how big they look, but by how much they weigh, mass without size, weight without shape. One of the strangest kinds of smallness the universe seems to allow. Einstein's equations, the same ones that gave us black holes almost by accident, have also been tested gently and repeatedly in far calmer, far closer settings than the edge of a collapsed star, and every single test so far has agreed with them. The planet Mercury's orbit around the Sun wobbles very slightly more than ordinary Newtonian gravity alone can explain, a subtle drift in its closest approach point that puzzled astronomers for decades until Einstein's equations accounted for it perfectly, on the very first try, using no adjustable numbers at all, simply falling out of the deeper geometry of curved space around the Sun. Starlight passing near the Sun during a solar eclipse in 1919 was measured to bend by just the amount Einstein's equations predicted, a result that made headlines around the world and turned a quiet German physicist into an overnight household name. Even the satellites hovering above your head right now, quietly beaming down the GPS signals that guide people to unfamiliar addresses, must correct for the fact that time runs very slightly faster for them, high above Earth's gravity, than it does for you lying still in your bed tonight. A correction of only a few dozen millionths of a second each day that would, left unaccounted for, cause GPS positions to drift by miles within a single day. Proof. Tucked quietly into an ordinary phone in an ordinary pocket, that the same warped, patient geometry describing black holes far across the universe is also gently, invisibly, constantly at work right here, holding your own small corner of space and time together in exactly the shape it should be. Stephen Hawking spent much of his working life thinking about black holes from a wheelchair, diagnosed in his early 20s with a condition that gradually took away his ability to move and eventually to speak without the help of a computerized voice synthesizer. And yet somehow, working within a body that grew quieter and quieter over the decades, his mind kept reaching outward towards some of the loudest, most extreme objects in the universe, discovering that they leak radiation, popularizing their strange thermodynamics, and eventually writing a book meant for ordinary curious readers rather than only fellow physicists, called A Brief History of Time, which quietly became one of the best-selling science books ever published, carrying the strange, dark, beautiful idea of black holes out of physics departments and into millions of ordinary homes, onto millions of ordinary nightstands, sitting there, unread by many past the first few chapters if we are honest about it, but present all the same, a small quiet monument to how deeply an entire species can become fascinated with objects it can never see directly and can never visit. Black holes have wandered into stories and films exactly the way they wander gravitationally into everything else nearby, pulling imaginations in the way they pull light. And one of the more careful and beautiful examples arrived in a film called Interstellar, whose depiction of a fictional black hole named Gargantua was built, unusually for a movie, using real physics equations worked out by the same physicist, Kip Thorne, who once bet on Cygnus X1 being real, producing a visual of gravitational lensing so accurate that the resulting images actually taught working physicists a few new details about how light bends around a spinning black hole's photon sphere, a rare case of a movie screen quietly feeding a small, genuine discovery back into the world of actual published science. Proof that a story meant only to entertain can sometimes still whisper something true. One of the loveliest and least intuitive facts to carry gently into sleep is this. The difference between falling forever and orbiting safely around a black hole is, once you are far enough away, exactly the same as the difference between falling forever and orbiting safely around anything else of equal mass. A spacecraft could orbit a black hole the same size as our Sun in exactly the same lazy, stable ellipse the Earth traces around our actual Sun today, requiring no unusual fuel, no special shielding, no dramatic maneuvering, simply obeying the same quiet orbital mechanics spacecraft already obey around ordinary planets and stars, right up until, if it chose to, it drifted too close, past the point where orbits stop being safe and start being a slow, patient invitation toward the event horizon instead, a boundary that exists around every gravitating object in the universe, black holes included, called the innermost stable circular orbit, past which even a small nudge closer begins an unstoppable spiral inward. Though for anything much farther out, the black hole is, gravitationally speaking, one of the least dramatic neighbors you could ask for, simply pulling exactly as hard as its mass says it should, nothing more, nothing sudden, nothing unfair. There's a particular kind of quiet available only very late at night, the kind that comes from realizing that everything you have just been drifting through, the collapsing stars, the frozen light at the horizon, the slow evaporating whisper of Hawking radiation, the patient orbits of stars around a hidden giant at the center of our own galaxy, the first blurry photograph of a shadow 55 million light years away, all of it is happening right now, at this very moment. While you lie here comfortable and warm, and slowly losing the thread of your own thoughts. Somewhere above the roof of wherever you are resting, invisible and utterly indifferent to whether anyone notices, black holes are quietly bending starlight, slowly leaking their last few atoms of radiation into an emptiness that will not notice for longer than any calendar can meaningfully describe, holding their secrets not out of any desire to keep them, but simply because that is what the deepest geometry of gravity does when enough mass gathers in one patient, quiet place. Curling space closed around itself, the way a hand curls gently closed around something small and easily lost, holding it, without meaning to, forever. The instrument that finally captured that first blurry photograph of a black hole shadow was not really a single telescope at all, but something far stranger and lovelier. A collaboration called the Event Horizon Telescope, stitched together from radio dishes scattered across Hawaii and Arizona and Mexico, and Chile and Spain, and even Antarctica, all listening to the exact same patch of sky at the exact same moment. Their individual signals later combined by careful computer processing into the resolving power of a single telescope roughly the size of the entire Earth, because no single dish, however large, could ever be built wide enough on its own to resolve something as small and as distant as a black hole's shadow. And so, instead of building one impossibly large eye, astronomers borrowed dozens of ordinary eyes scattered across an entire planet and taught them to blink together in perfect, practiced unison, turning the whole Earth itself into the lens. The data collected during those observing nights was so enormous, many thousands of hard drives full, that it could not simply be sent over the internet in any reasonable time, and instead had to be physically flown, drive by drive, continent by continent, back to central processing centers, meaning that in a lovely, almost old-fashioned twist, one of the most advanced scientific images ever produced depended, in its final steps, on ordinary airplanes carrying ordinary boxes of hard drives the same unglamorous way a package might carry anything else across the world, patient cargo holding, without any of the airline staff realizing it, the very first true picture of a black hole's shadow, still waiting quietly to be assembled. Somewhere out among the more unusual black hole systems astronomers have found is a distant object called OJ 287, where a supermassive black hole weighing billions of times as much as our Sun is orbited by a smaller companion black hole on a long, looping, egg-shaped path that carries it plunging through the larger one's surrounding disk of gas roughly twice every 12 years, each plunge triggering a bright, predictable flare of light that astronomers have now successfully forecast in advance more than once. A pair of black holes locked in a slow, repeating, cosmic waltz so regular that humans watching from many thousands of light years away can set their calendars by it. A strange kind of clockwork built from gravity and gas, and two objects that will, very many millions of years from now, eventually spiral together and merge the way so many pairs of black holes eventually do. There is a deep and delicate idea called the holographic principle that grew directly out of thinking carefully about black hole entropy, the strange discovery that all the hidden information behind an event horizon seems to scale not with the volume tucked inside, the way you might ordinarily expect, but instead with the area of the horizon's surface itself, as though everything happening inside a three-dimensional region could, in principle, be completely described by information smeared across its two-dimensional boundary. Instead, the way a hologram printed on a flat card can still produce the illusion of a full three-dimensional image when you tilt it in the light. Some physicists now wonder, gently and without yet any full proof, whether this strange property of black holes might be hinting at something true about the whole universe, that reality itself might, at its very deepest level, be organized more like the surface of some greater boundary than like the solid, filled in volume it appears to be from the inside, an idea strange enough to make your head spin gently on the pillow, and calm enough if you let it, to spin you gently right on into sleep, instead of keeping you awake worrying over it. Within our own Milky Way alone, astronomers estimate there could be as many as 100 million stellar mass black holes drifting quietly among the galaxy's hundreds of billions of stars, the scattered leftover hearts of countless massive stars that lived fast and died young over the galaxy's long history. And yet only a small handful of these have ever actually been confidently identified and located, simply because an isolated black hole drifting alone through space, not currently feeding on any companion star, gives off no light at all and betrays its presence only through the rare, brief gravitational lensing flicker it causes if it happens to drift in front of some distant background star, meaning that the overwhelming majority of black holes in our own galactic backyard are, and may always remain, quietly and permanently invisible to us, felt only in aggregate through statistics and calculations, never once actually seen. Some black hole systems announce themselves not through a single quiet flicker, but through a bright, steady glow that first drew astronomers' attention long before anyone understood what was producing it, called X-ray binaries, systems where a black hole and an ordinary living star orbit closely enough that the black hole's gravity siphons gas directly off the outer layers of its unlucky neighbor, pulling a slow, steady stream of stellar material into a bright, feverish accretion disk that glows fiercely in X-rays, sometimes flickering and varying on timescales of mere seconds, a companion star spending the rest of its life slowly, patiently donating pieces of itself to its invisible neighbor. The two of them locked together in an orbit that will only end once the donor star has given away so much of itself that it can no longer sustain the exchange. An oddly intimate, oddly patient kind of cosmic relationship playing out in complete silence, over spans of time long enough to make an entire human civilization rise and fall before any noticeable change could be measured. Think for a moment, gently, about how strange it is that despite everything astronomers have learned, the actual interior of a black hole, everything beyond its event horizon, remains and will very likely always remain permanently unobservable from the outside, not because our instruments are not good enough yet, the way an old telescope might simply need a better lens, but because the very geometry of the event horizon itself forbids any signal, any light. any information whatsoever from ever climbing back out to tell us what it saw. This means that in the truest, deepest sense, a black hole's interior is not merely a place we have not yet visited, the way the bottom of the deepest ocean trench was unvisited before submarines were invented, but a place that is, by the very laws that create it, permanently sealed away from ever being reported on. The most private, most unshareable secret the universe is capable of keeping, hidden not out of any decision but simply because that is what it means, mathematically and physically. For gravity to have won so completely, in one small, patient region of space. And yet, drifting back outward now, away from that sealed and private interior and toward the wide, dark, gentle spaces between the stars, remember that every black hole, no matter how violent its birth or how extreme its gravity, ultimately does something rather calm with its existence once it has settled into its role. It simply curves the space around it exactly the amount its mass requires, quietly, consistently, without exception, for as long as it exists, asking nothing of the universe except to be allowed to keep doing that one patient job for a very, very long time, longer than stars, longer than galaxies in some cases, longer than nearly anything else the universe will ever produce. The detectors that first heard two merging black holes chirp softly across a billion light-years of empty space were themselves small miracles of quiet, patient engineering, each one shaped like a giant L, with two arms each 4 kilometers long, laser light bouncing back and forth inside vacuum tubes so carefully isolated from every passing truck, every distant earthquake, every gentle ocean wave breaking on a shore hundreds of miles away, that the only thing left able to disturb them, on a good quiet night, was the very thing they were built to detect, a ripple in space itself smaller than the width of a single proton spread out over the entire 4-kilometer arm, meaning the detector had to be sensitive to a change in length so small that if you scaled the whole arm up to the distance between the Earth and the nearest star, the ripple it was hunting for would still only be about the width of a human hair, an act of engineering patience almost as extreme, in its own quiet human way, as the gravity it was built to listen for. Engineers and astronomers are already dreaming of even larger ears to listen with, including a proposed space-based detector called LISA, short for Laser Interferometer Space Antenna, which would place 3 spacecraft in a slow, patient triangular formation millions of kilometers apart, bouncing laser light between them across that vast gap in order to listen for gravitational waves far too low and far too slow for any ground-based detector to ever catch. Waves produced not by small stellar black holes merging, but by enormous supermassive black holes, the kind sitting at galactic centers, slowly spiraling together over years or decades, rather than the final fraction of a second astronomers currently listen to. A deeper, slower, more patient hum waiting quietly for a large enough and quiet enough ear to finally be built for it, sometime in the years ahead. Even now, without any space-based detector yet in orbit, astronomers have found an ingenious way to listen for the very slowest and lowest gravitational hum of all, produced not by any single pair of merging black holes, but by the combined, overlapping murmur of countless supermassive black hole pairs slowly orbiting each other throughout the universe, a background hum sometimes called the gravitational wave background. To listen for it, astronomers use pulsars, the same rapidly spinning collapsed stellar cores that sweep beams of radio light across space with the steady, dependable regularity of the most precise clocks nature has ever built, watching for the tiniest, most patient irregularities in the arrival times of those beams caused by gravitational waves gently stretching and squeezing the space between the pulsar and the Earth. And in 2023, after using this method patiently for more than 15 years across telescopes scattered around the world, astronomers finally announced convincing evidence of exactly this background hum, the sound, in a sense, of countless slow, ancient, supermassive black hole pairs murmuring quietly to each other across the entire observable universe, a hum older and slower and far more widespread than any single chirp ever caught before. Black holes rarely act entirely alone, and hierarchies of them sometimes build up gradually inside dense environments like globular clusters, tightly packed swarms of very old stars orbiting the outskirts of galaxies, where the crowded, busy gravitational dance of so many stars in a small space naturally encourages some of them to sink toward the cluster's center over time and occasionally pair up and merge. Black hole meeting black hole meeting black hole, growing step by patient step. Generation after generation, in a slow hierarchical climb from ordinary stellar remnants toward something heavier and rarer. One of the leading theories for how those elusive intermediate mass black holes mentioned earlier might quietly come to exist tucked away at the crowded hearts of these ancient stellar swarms. If you tried to imagine the entire mass of a supermassive black hole compressed down to a single grain of sand instead, and asked how far away you would need to stand for its gravity to feel like ordinary Earth gravity beneath your feet, the answer would be almost too close to measure, because a grain of sand carries essentially no mass at all compared to billions of suns, and this small, almost silly thought experiment is worth carrying gently into sleep, because it reminds you that black holes are not frightening because of some magical density trick alone, but simply because so very much ordinary mass, the same kind of mass making up your own body and your own bed and the walls around you right now, has been gathered into so very little space, gravity behaving exactly as it always does, only now with far more weight than usual concentrated far closer together than usual. Nothing supernatural, nothing magical, only ordinary physics taken to an extraordinary, patient extreme. Every confirmed gravitational wave detection is given a quiet, almost bureaucratic-sounding name, a code built from the date it was detected, so that the very first one ever caught, that historic chirp from September 2015, carries the plain, unglamorous label GW150914, and every detection since has followed the same simple pattern, a small reminder that even the most extraordinary discoveries in physics often get filed away, in the end, with names about as sleepy and unremarkable as a library catalog number, the actual wonder living quietly inside the data itself, rather than in whatever label gets stamped on the outside of the file. Let your thoughts settle for a moment on just how old some of this light and gravity really is by the time it reaches us. The light captured in that first black hole photograph left the galaxy M87 roughly 55 million years ago, long before any human being existed to build a telescope capable of receiving it, back when the ancestors of modern humans were still small, tree-dwelling creatures, barely beginning to separate from other primates. Meaning the photograph you might have glanced at once online was not a picture of something happening now, but a picture of something that happened in a past so distant it predates almost the entire story of our own species. A snapshot mailed across the universe 55 million years ago, and only just now, in your own lifetime, finally arriving to be opened. And the gravitational waves from that very first detected black hole merger back in 2015 had been traveling toward Earth for even longer still, more than 1 billion years. Meaning the two black holes that produced that chirp finished their spiraling dance and merged into one back when the only life on Earth consisted of simple single-celled organisms drifting quietly through ancient oceans, long before anything resembling an animal, let alone a person, let alone a bed, let alone a blanket, existed anywhere on this planet. And that single ancient ripple traveled patiently through the emptiness of space for that entire span of time, through the entire rise of complex life, through the entire age of dinosaurs, through the entire slow climb of mammals, and then humans, and then civilizations, arriving at the exact right moment to be caught, almost impossibly precisely, by two newly finished detectors on the exact same day astronomers had finally finished tuning them well enough to listen. Let your breathing slow again for a moment. In and out, in and out. The way the universe itself seems to breathe on the longest timescales, expanding, cooling, stars igniting and dying in slow waves across billions of years, and rest for a while on the idea of failed supernovae, a quieter and stranger way for some black holes to form than the bright, explosive collapse described earlier. Astronomers watching certain massive, aging stars through their telescopes have, on a small handful of occasions, watched a star that should have exploded in a brilliant supernova simply dim, quietly and almost apologetically, fading out of sight over the course of a few months without any explosion at all, as though the star had simply lost its nerve at the last moment and slipped away instead of announcing its ending the usual dramatic way. The entire outer layer of the star falling directly inward to join the collapsing core rather than being blown outward into space, producing a black hole with, in a strange sense, no fireworks at all, only a slow fading, a star quietly excusing itself from the room rather than making any kind of scene on its way out. The very shape of the glowing ring photographed around a black hole's shadow is not actually the same size as the event horizon itself, but instead traces out the photon sphere mentioned earlier, which sits at about 1.5 times farther out than the horizon for a simple non-spinning black hole, meaning the dark shadow visible in these photographs is actually noticeably larger than the true, absolute boundary of no return hidden quietly inside it, a small, gentle detail that matters quite a lot to careful astronomers and matters barely at all to the rest of us drifting sleepily along, except as one more reminder that even the most extreme darkness in the universe still casts a shadow slightly larger than its truest, most private self. Quasars, those blazing, distant, black hole-powered beacons mentioned earlier, turn out to double as some of the most useful tools astronomers have for measuring the universe's own expansion, because their light, stretched and reddened by the ever-growing distances of an expanding universe on its long journey toward us, carries within it a kind of built-in odometer called redshift. Letting careful measurement of a quasar's light tell astronomers not only how far away it is, but how long ago its light actually left, turning some of the universe's most violent, most extreme black hole-powered objects into some of its most useful, most gentle mile markers, quietly helping measure the size and age and history of everything else around them simply by shining so reliably and so brightly across such enormous, patient distances. Far off in the extremely distant future, long after every star still burning tonight has quietly gone dark, astronomers expect the universe to enter what some have gently nicknamed the black hole era, a vast stretch of time, so long it makes even the current age of the universe look like a single, brief breath, during which black holes will be nearly the only objects left with any structure at all, drifting slowly through an otherwise cold and empty universe, glowing ever so faintly with their last patient traces of Hawking radiation, merging occasionally when their slow paths happen to cross, and finally, one by one, evaporating away entirely, the largest and heaviest going last, outliving everything else the universe ever built, patient right up until their own final, faint, silent fade into nothing, the last lights of a very long, very quiet story finally switching off, with nothing left afterward to even notice they were gone. Before that impossibly distant ending, though, there was also a beginning, and it is worth drifting back once more, gently, to the very early universe, to time astronomers sometimes call the era of population III stars, the first generation of stars ever to form, built entirely from hydrogen and helium left over from the Big Bang itself, with none of the heavier elements like carbon or oxygen or iron that later generations of stars, including our own sun, inherited from all the stellar deaths that came before them. These very first stars are thought to have been extraordinarily massive, some many hundreds of times heavier than our sun, burning fast and dying young, and many of them likely collapsed directly into some of the very first black holes the universe ever produced, ancient seeds planted in the first few 100 million years after everything began, patiently waiting through the long history that followed to grow, through feeding and merging, into some of the enormous supermassive giants we now find anchoring galaxies today. Gravitational waves, it turns out, come in more than one simple shape, another small, quiet detail tucked into Einstein's equations. As a wave passes through a region of space, it stretches space in one direction while simultaneously squeezing it in the perpendicular direction, then reverses over and over in a pattern physicists call a plus polarization, though general relativity also predicts a second possible pattern, rotated at an angle called a cross polarization, and detecting both patterns together. Using a whole network of detectors spread across different continents, including one built in Italy called Virgo and another in Japan called KAGRA, lets astronomers not only confirm a gravitational wave passed by, but actually work out, from the combined pattern across multiple distant detectors, roughly which direction in the sky it came from, turning a handful of scattered, patient instruments into something like a very slow, very careful set of ears working together to point, gently and approximately, back toward the source. The idea that a black hole might cast any kind of visible shadow at all was not simply invented, once telescopes finally became good enough to check. Theoretical physicists had worked out, decades in advance, almost exactly what such a shadow should look like, calculating the expected shape and size of the dark region and its surrounding photon ring long before any instrument existed capable of actually seeing it, meaning that when the real photograph finally arrived in 2019, it was not really a moment of surprise so much as a moment of quiet, satisfying confirmation, a hand-drawn prediction, made carefully with pencil and equation many years earlier, finally checked at last against reality and found, gently and precisely, to have been right all along. Rest here a while longer if you like, on the simple, repeating shape of so much of this story. Something ordinary, a cloud of gas, a star, a swirl of dust, gathers and gathers under its own patient weight, until eventually gravity wins completely, and what is left behind curves the space around itself so thoroughly that light itself agrees to stay. And then having formed, that quiet, dark, curved place simply waits, sometimes for a moment on a cosmic scale, sometimes for a length of time longer than anything else in existence will ever last, glowing faintly, bending starlight gently, humming almost imperceptibly whenever two of its kind finally meet and merge, asking nothing, expecting nothing, simply continuing to exist in exactly the shape its own mass requires, for as long as mass and gravity and the patient darkness between the stars allow it to. There's something almost tender about the way astronomers first learned to find black holes they could never directly see, back before any picture existed, back before gravitational waves had ever been caught, relying instead on the quiet, careful, patient business of watching how ordinary visible things behaved nearby, the wobble of a companion star's light being tugged rhythmically back and forth, the flicker of X-rays betraying a hidden feeding disk, the graceful decades-long orbits of stars swinging around a point where nothing at all could be seen, each one a small act of trust in mathematics over eyesight, a willingness to believe in something invisible simply because everything visible around it kept moving exactly the way an unseen, patient wait would make it move, the same quiet logic in its own way that lets you trust the wind is real on a dark night even with your eyes closed, simply by feeling how gently it moves the curtain. Consider, too, how strange and lovely it is that the very same equations describing the most violent, most extreme collapse a star can undergo also describe, with only the smallest of adjustments, the gentle curve of space around your own body right now, the same warping of space and time that makes a dropped feather drift slowly to the floor instead of hanging forever in the air, the same patient geometry that keeps your own 2 feet resting against the mattress beneath you, holding you here, gently. The whole time you have been drifting through this long, slow story, gravity never once taking a break, never once needing to choose between holding a galaxy together and holding you steady in your own quiet bed, simply doing both, everywhere, all the time, without favoring one over the other, without effort, without any sound at all. Somewhere out past the edge of easy imagining, black holes continue to merge tonight, exactly as they have merged for billions of years before tonight, and will keep merging for billions of years after, sending out ripples that will not arrive anywhere for ages longer than any current instrument could wait around to catch. Ripples that will eventually wash gently over some far future detector built by people who do not exist yet, using techniques not yet invented, confirming truths about events that, by the time anyone notices them, will already be so ancient that whatever stars still glowed at the moment of the original collision will themselves have long since faded. A message sent across time so patiently and so slowly that its eventual reader will belong to an entirely different chapter of the universe's long story than its original sender ever did. And still, none of this needs to be carried too heavily into sleep tonight, because for all their strangeness, black holes are, in the end, simply one more kind of quiet thing the universe makes when it has enough time and enough patience and enough gravity to work with, no stranger in their own way than the quiet, patient work of an ordinary river carving a canyon over millions of years, or frost slowly cracking a stone over many freezing winters, simply gravity. Given enough mass and enough stillness, doing the most gravity thing it possibly can, curling a little pocket of space closed around itself, and then settling in, calm and dark and unbothered, to wait. Let the story rest here for a while, drifting gently rather than reaching for anything more just yet. The way a walk sometimes needs to slow down near the end, not because the path has run out, but simply because the walker has grown pleasantly, comfortably tired, and there is no reason at all to hurry the last stretch home when the whole point of the evening was always the walking itself, slow and unhurried and quiet, one soft observation gently following another. The vast dark sky continuing to hold its secrets exactly as patiently as it always has, whether or not anyone is still awake to keep listening. Somewhere far above you, whether the sky tonight is clear or clouded, hidden or visible, the same slow, ancient, patient darkness is still doing exactly what it has always done, curving quietly around itself in 100,000 hidden places you will never see and never need to see. And there is a kind of comfort in that, the same comfort found in knowing a lighthouse keeps turning even on nights you are not awake to watch it. A black hole needing no audience at all to keep existing exactly the way it does, faithful to nothing but its own gravity, constant in a universe where almost everything else eventually changes, fades, or ends. Rest now a little further into the hush between one thought and the next, the same hush that fills the space between stars, the same hush that will fill, someday, the very last moments of the very last black hole's very last whisper of radiation. A hush that is not empty so much as simply patient, waiting the way you are waiting now, comfortable, unhurried, ready, whenever you are ready, to finally let go of the thread of this story and drift, gently, the rest of the way down into sleep. But if your eyes are still resting open just a little, if your mind is still floating comfortably along rather than sinking all the way down yet, there is still more of this quiet, dark story left to wander through, more strange, soft corners of the universe worth visiting before the night is done. Because black holes, patient as they are, still have a few more secrets left to whisper before we finally let the story close. Think, for a moment, about the smallest possible size a black hole's boundary could take for any given amount of weight, a size physicists calculate with a simple, almost lullaby-plain formula, and call the Schwarzschild radius, named quietly after that same physicist who found the very first solution to Einstein's equations while serving on a distant battlefield. For an object exactly as heavy as the Earth, that radius works out to be smaller than a single grape, meaning if you could somehow, impossibly, compress the entire planet Earth, every ocean, every mountain, every quiet bedroom on it, down into a sphere smaller than a grape, without losing a single ounce of its mass, it would become a black hole, its own gravity finally winning completely over whatever material had been holding it open and round before. For the Sun, as mentioned earlier, that same radius stretches out to about 4 miles, and for the supermassive giant at the center of our galaxy, it stretches out to a boundary wider than the orbit of Mercury around our own sun. A single, quiet formula scaling all the way from a grape to a solar system, depending only on how much weight you feed into it. Near the very edge of what a rotating black hole's mathematics allows, physicists have found strange, delicate solutions describing something called closed time-like curves, paths through spacetime that, at least on paper, loop back around to their own starting point, raising the old, familiar, dizzying question of whether something might, in some far corner of a spinning black hole's inner geometry, revisit its own past. Almost every physicist who studies this carefully suspects that real, physical black holes, the actual collapsed stars and galactic giants out there in the real universe, do not actually contain any usable version of this strange loophole, that the inner regions where such loops might appear in the pure mathematics are hidden behind additional layers of instability and disruption that a real, messy, non-ideal collapse would never actually produce cleanly enough to use. But the fact that the equations even whisper the possibility at all, tucked deep inside the geometry of a spinning collapsed star, remains one of the strangest, most delicately dreamlike details in this entire quiet subject. A locked door imagined so precisely that we can describe its hinges perfectly without ever actually being able to open it. There is a gentler, calmer cousin to the information paradox called black hole complementarity, an idea suggesting that the strange disagreement between what a falling observer experiences crossing an event horizon, nothing unusual at all, and what a distant observer calculates happening at that same horizon, information seemingly burning up and re-radiating outward, might not actually be a true contradiction at all, but simply two descriptions that are each completely valid for their own observer and simply can never be compared side by side, because no single observer could ever be in a position to check both stories against each other at once, the falling traveler already gone beyond any possibility of reporting back, the distant observer never able to follow across to verify anything firsthand. Two honest witnesses describing the very same quiet event so differently that only the impossibility of ever cross-examining them both keeps their stories from technically disagreeing at all. A more unsettling cousin of that same idea, called the firewall paradox, wonders whether the smooth, gentle, uneventful crossing of a horizon described earlier might not actually hold up under the most careful quantum mechanical scrutiny. Some physicists calculating that a sufficiently old black hole, one that has already radiated away a great deal of its original information through Hawking radiation, might instead present a falling traveler with a wall of extremely high energy. Quite unlike the gentle nothing described in the friendlier version of this story, right at the horizon itself. This disagreement remains genuinely unresolved among physicists today, a rare and honest admission at the very frontier of this field that despite a century of careful work, nobody yet knows for certain, down to the very last quantum detail, exactly what crossing a black hole's edge would actually, truly feel like. A small, honest gap in an otherwise remarkably well-confirmed theory, patiently waiting for someone someday to close it. Physicists chasing an even deeper theory of gravity, one that would finally stitch Einstein's smooth, curved description of spacetime together seamlessly with the strange, probabilistic rules of quantum mechanics that govern atoms and particles, have offered a few different patient guesses at what such a theory might look like, including one approach called string theory, which imagines that the smallest building blocks of everything are not points at all but tiny vibrating loops, and another called loop quantum gravity, which imagines that space itself, rather than being smooth and continuous the way it feels lying here in your bed, might actually be built from tiny discrete grains at the very smallest possible scale, far too small for any instrument to ever directly detect, the way a photograph looks perfectly smooth from a distance, but is secretly made of countless individual dots up close. Neither approach has yet been confirmed by any experiment, and black holes, precisely because they are the one place in the universe where gravity's smooth curves and quantum mechanics strange, grainy rules both matter enormously at the very same time, remain one of the most promising places physicists hope, eventually, some careful new observation or some elegant new insight might finally help tell these competing guesses apart. One particular star, known simply by the plain, quiet label S2, has been watched by astronomers for more than 2 decades as it swings around Sagittarius A star in a long, looping orbit, swooping in at its closest approach to a distance, still many times farther than Mercury is from our own Sun, but moving at that closest point at nearly 3% of the speed of light, fast enough that careful measurements of its motion have let astronomers confirm, with remarkable precision, both the black hole's mass and several subtle predictions of general relativity, including a gentle, gradual rotation of the star's own orbital path over time, called a Schwarzschild precession, the same basic kind of orbital shift Mercury shows around our Sun, but scaled up enormously by the far stronger gravity so much closer to a far heavier, hidden companion, one patient, well-behaved star, quietly proving, orbit after orbit after orbit, that the invisible giant it circles is exactly as heavy and exactly as strange as the equations always said it must be. Our own Milky Way is not the only galaxy with a quiet giant at its heart, of course, and our nearest large neighbor, the Andromeda Galaxy, harbors a supermassive black hole of its own, somewhat heavier than our own galaxies, sitting there patiently at the center of a galaxy that is itself slowly, gently falling toward our own across a span of several billion years, the two galaxies eventually destined to merge into one another in the distant future. Their central black holes very likely destined, many billions of years from now, long after our Sun has swollen and faded and gone quiet itself, to spiral together and merge as well, one final, enormous, patient collision between the two quiet giants that once sat at the hearts of two separate galaxies, becoming, eventually, only one. Before that grand collision, though, astronomers can already study something almost like a smaller preview of it happening much closer to home, in a variety of colliding galaxy pairs scattered across the observable universe, some caught mid-collision, their stars and gas clouds streaming into long, glowing tidal tails, while their central black holes drift slowly closer together at the heart of the wreckage. And in a few especially rare and treasured cases, astronomers have caught sight of two separate, actively feeding supermassive black holes glowing side by side within a single, disturbed galaxy, a pair of quiet giants not yet merged but clearly, patiently, gravitationally aware of each other, caught in that slow, multi-million-year orbital dance that will, given enough patient time, eventually end the way so many of these stories end, in one final, gentle, gravitational wave-releasing merge. One of the loveliest kinds of black hole discoveries in recent years has come not from watching stars glow, but from watching them very quietly refuse to glow at all, or rather from watching a completely ordinary, visible star wobble in its position against the background sky in a way that reveals an invisible companion tugging on it. This method, called astrometric detection, was used to help confirm one of the closest known black holes to Earth, a quiet, otherwise unremarkable stellar system where a perfectly ordinary star was found, through years of extraordinarily precise position measurements from a satellite mapping the positions of nearly 2 billion stars across the galaxy, to be wobbling in a smooth, repeating pattern that could only be explained by an invisible black hole companion roughly 9 times heavier than our Sun, orbiting quietly, unseen, close enough to have been hiding in plain sight the whole time, simply waiting for measurements precise enough to finally notice its patient, invisible tug. Even the very method used to first prove Sagittarius A star's mass, watching the graceful decades-long orbits of stars near the galactic center, required an extraordinary kind of patience from the astronomers themselves. Entire scientific careers spent returning, year after year, to the very same patch of sky, refining the same telescopes, gathering the same kind of image again and again, slowly accumulating enough data points to trace out, one small dot at a time, the graceful, curving arc of an orbit that takes many years to complete even a small fraction of, the kind of research that rewards not quick brilliance alone, but a very particular, very rare kind of scientific patience. The willingness to watch the same quiet point in the sky for the whole of one's working life, and trust that the picture would eventually, gradually, become clear. Telescopes being built and planned right now promise to make the coming years an especially rich time for this whole quiet field, including a massive new observatory named for astronomer Vera Rubin, whose careful measurements of galaxy rotation decades ago first hinted strongly at the existence of dark matter, and which is expected, once fully operating, to survey the entire visible sky repeatedly, catching countless tidal disruption events and gravitational lensing flickers that would otherwise have gone unnoticed, along with a space telescope named for Nancy Grace Roman, one of NASA's first female executives, designed in part to hunt for exactly the kind of gentle, background gravitational microlensing flickers that might, patiently, over years of watching, finally reveal a meaningful census of those isolated, rogue, invisible stellar mass black holes drifting quietly through our own galaxy that have so far mostly escaped detection. Radio astronomers, too, dream of an even larger version of the patient, Earth-spanning trick that produced the first black hole photograph, in the form of a future project called the Square Kilometer Array, which would link together thousands of individual radio dishes and antennas across 2 continents into a single combined instrument of enormous collecting power, promising, among many other things, an even sharper eventual view of the swirling material around nearby supermassive black holes. And perhaps, someday, radio evidence of that slow, ancient gravitational wave hum produced by countless distant supermassive black hole pairs, heard even more clearly than the first patient hints astronomers only recently, carefully, finally began to detect using pulsars alone. A rotating black hole, it turns out, cannot spin arbitrarily fast no matter how much spinning material falls into it, because there exists a natural upper limit called the extremal limit, beyond which the mathematics describing its event horizon would break down into something physicists strongly suspect nature simply never allows to happen: the spin, and the mass needing to stay in a careful, patient balance with each other. The way a figure skater can only pull their arms in so far before their own body simply cannot spin any faster without flying apart, gravity itself apparently imposing its own quiet, careful speed limit on how energetically any black hole is allowed to turn, a limit that keeps even the most extreme spinning giants from ever quite crossing into a stranger, more troubling mathematical territory where an event horizon might vanish entirely and leave something altogether more exposed and unruly behind. Even the seemingly simple question of how many black holes exist across the entire observable universe turns into a strangely dreamy kind of arithmetic once you actually try to answer it. Astronomers estimating, from careful counts of galaxies and reasonable guesses about how many black holes each one likely holds, that there may be somewhere on the order of 40 octillion stellar mass black holes scattered throughout the observable universe. A number so large that writing all its zeros out in a row would stretch itself into its own small, strange kind of poem, more black holes, by that rough and patient estimate, than there are grains of sand on every beach and desert on the entire Earth combined, each one formed the same quiet way: a star's fuel running low, a core collapsing, a small dark patient pocket of curved space settling in where a star used to shine, repeated across the universe more times than any person could ever hope to count, even across an entire lifetime spent trying. And yet, for as many as there may be, scattered thickly across the whole observable universe, the actual amount of space any single black hole physically occupies remains, by cosmic standards, almost comically small, meaning that despite there being untold octillions of them, the overwhelming majority of the universe, by an enormous margin, remains simply open, empty, quiet space, stars scattered thinly through it like a few grains of sugar stirred into an enormous glass of water. Black holes in EV,